Differential equations, type 2 real-world problems. A, linear motion. So before we can start our examples on linear motion, we just have to remind ourselves what our letters are going to represent. So S is displacement and its unit is meters. V is velocity and its unit is meters per second. A is acceleration and its unit is meters per second squared. D is time and its unit is seconds. So if we were to define velocity, we would say it's the change in distance over time. Or we can also say that it's the rate of change of velocity or rate of change of displacement with respect to time. And if we were looking at acceleration, we would say it's the change in velocity over time taken, or the rate at which the velocity is changing with respect to time. But the other thing that we can say about acceleration is that it's also the second derivative. So d squared s dt squared, or quite commonly in applied maths in this question 10, we'll be using the fact that A can also be written as V times dV ds. And that's because if we look, V is ds dt. So therefore, if I have V, which is ds dt, multiplied by dV ds, well, our ds's would cancel, and that would leave us with dV dt, and of course dV dt is acceleration. So therefore we say A is equal to V dV ds. So depending on what information is going to be given to us in the questions, we will either use acceleration is dV dt, or that acceleration is V dV ds. We will always use velocity is ds dt. So the example we're going to do is from Oliver Murphy's book, page 217. So exercise 12I, question 1. And we're given a particle P starts from a point P with an initial velocity of 2 meters per second, moves in a straight line subject to an acceleration which is equal to v squared plus 4 meters per second squared, where v is our velocity. And we have to find, correct to 2 decimal places, the time taken to reach 6 meters per second, using the fact that acceleration is equal to dV dt. So the information we're given here then is that acceleration we're going to be writing as dV dt, but we know that our acceleration is given by v squared plus 4. So therefore that means that v squared plus 4 must equal dV dt. So we're going to separate out our v's and our dv on one side and our t's and our dt on the other side. So of course that gives me 1 over v squared plus 4 if I divide across by v squared plus 4. And then if I multiply both sides across by dt, I just get 1 dt. So now we're ready to integrate. So if I integrate the left with respect to v, and I integrate the right with respect to t, all I need now are my limits. So what do I know at the start and what do I know at the end? Well, we're told at the start that it starts from a point P with an initial velocity of 2 meters per second. So if it's starting from a point P and we're integrating the left with respect to v, then I need limits for velocity. So that's starting velocity is 2. And then it's the time taken to reach 6 meters per second, which means at the end, the velocity reached is 6 meters per second. Now, if I look at the right-hand side of this equation here, it's with respect to time. So therefore, my other limits that I need to look at are time taken. So if it's starting from point P, that means we would take the initial time to be 0 seconds. And the end time is what I'm looking for, so therefore I don't know what it is. I need to find it correct at 2 decimal places, so I'm going to be putting in my limits in terms of t. So my end limits are always my upper limits, and my start limits are always my lower limits. And now we're ready to integrate. So we have to recognise the function on the left-hand side, and we can see it's 1 over something squared plus something squared, which means it must be tan inverse. So if we go to page 26 in our tables, we can see here tan inverse there in the middle. So therefore that's going to be written as something squared, so v squared plus something squared, which is 2 squared dv. And therefore, in that equation, it's a is going to be 2. So in other words, that's going to be 1 over a, so 1 over 2, tan inverse of x over a, so in this case, v over 2, and that's within the limits of 6 and 2, and that's going to be equal to t. So if I integrate 1 with respect to t, I'm going to get t. So now subbing in my limits, I have a half times tan inverse of v over 2, so that's going to be 6 over 2, minus a half tan inverse of 2 over 2, and that's equal to t minus 0. So in other words, we're going to have a half times tan inverse of 3 minus a half times tan inverse of 1 is equal to t. So we have to, of course, find t with respect to 2 decimal places. So if we put that into our calculator, making sure our calculator is in radians, and we get 0.23 seconds. So the reason it's called a one-step example is because we're getting from our given acceleration equation to our answer in one go. So we didn't need to kind of go from acceleration to velocity and then from velocity to displacement. So our second example. So this is going to be a two-step question, and that's because we're going to have to get there in 2 steps. So here we have a particle move so that its deceleration is equal in magnitude to the square of its velocity. It starts at point P with an initial velocity of 1/4 meters per second, and we're asked for how far will it travel after 8 seconds. So the reason we're going to have to do this in 2 steps is because we're looking for how far, which is s, and we're given our time, and we're given velocity. So therefore, we can't just go straight into finding s and t, because I would need a velocity equation, but I'm not given a velocity equation, I'm given an acceleration equation. In other words, I'm told that the acceleration is given by the square of its velocity, but it's deceleration, which means it must be minus v squared. So I'm going to let that equal to dv dt. Which means then if I set up my integral, I'm going to have minus v squared. I have to separate it out first. So I have 1 over v squared dv is equal to minus dt. And you can have the minus on the other side either, it doesn't make a difference. And if I set up my integral, then that's going to be v to the minus 2 dv is equal to the integrand of minus dt. So setting up my limits, my start limits, so my start velocity is, initial velocity is 1/4 meters per second. And the right hand side I'm integrating with respect to time, so starting from point P, which would be 0 time. And then the end limits, well, the velocity at the end, we don't know, so it's going to be in terms of v, and the time at the end is 8 seconds. So if I sub in my limits, sorry, that should say t, so we want a velocity equation. So my end limits v and t, initial limits are 1/4 and 0. So if I integrate the left-hand side there, I'm going to get v to the power of minus 1 over minus 1. So add 1, divide by the new power. And if I integrate minus 1 with respect to t, I get minus t within the limits of t and 0. So therefore that gives me minus 1 over v and minus t. And now if I sub in my limits, I have minus 1 over v minus 1 over a quarter, and then minus t minus 0. So in other words, I have minus 1 over v plus 4 equals minus t. So multiplying everything across by v there, or getting 1 over v on the left and everything else on the right. And now I can invert. I now have an equation that will represent the velocity at any given time. So the second step would be to find my displacement then. So step 1, find v. And then step 2 would be find s. So I've just found out that v is equal to 1 over t plus 4. So if I want s, well, I know v is equal to ds dt. So now I can rearrange to get my two equations. So I'll have ds is equal to 1 over t plus 4 dt. And now if I integrate both sides, and I look at my start and my end limits, well, at the start, we know our displacement is going to be 0, and the time will be 0, so it hasn't moved. And at the end, well, we're looking for s after 8 seconds. So end limits are our upper limits, and start is our lower limits. So if I integrate 1 with respect to s, I get s. And if I integrate 1 over t plus 4 with respect to t, well, we can go back here to page 26, and we see that that's our natural log function. So 1 over x. So 1 over a linear function is always natural log. So that's natural log of t plus 4, and that's within the limits of 8 and 0. So in other words, s minus 0 is just s, and then natural log of 8 plus 4 minus natural log of 0 plus 4. So that gives me natural log of 12 minus natural log of 4. And if I subtract my logs, I can divide. So that would be natural log of 12 over 4. So s is equal to natural log of 3 meters. And then if I was to give it correct to 2 decimal places, it could also be written as 1.1 meter. So depending on which way you want your answer in the exam or which way we're asked for, we can write it in either form. Natural log of 3 would be the exact value, 1.1 would be a rounded value. So on the sheet then you're going to do 97, 98 and 2000.